6 minutes ago, on a mountain in Chile, a camera the size of a small car opened its eye for the very first time, and in that single instant, it captured more of the observable universe than every astronomer in human history had recorded combined. Hidden inside that one photograph were things nobody had asked it to find. Objects that shouldn't have been visible, structures that shouldn't have existed on any map we had. And within hours, professional astronomers who had spent entire careers studying the night sky were staring at their screens, refreshing the same image, trying to convince themselves it was real. By the end of this video, you will understand exactly what was hiding inside that first photograph, why NASA and the National Science Foundation are calling it the most significant single image in the history of astronomy, and why some scientists believe we just watched the sky reveal more secrets in 10 hours than it gave up in the previous 10 years combined. Let's start with the morning that changed everything. On June 23, 2025, at 11 a.m. Eastern Time, in a live broadcast watched by scientists on every continent, the Vera C. Rubin Observatory released its first official images to the public. Not a test, not a simulation. Real light from real galaxies captured by a machine that had just spent years being built for exactly this moment. The observatory sits at 2,647 meters above sea level on a mountain called Cerro Pachón in northern Chile, chosen specifically because the air there is thin, dry, and almost perfectly still, the kind of atmosphere that lets starlight travel to a mirror without being scrambled on the way down. That mirror is 8.4 meters wide, engineered as a single combined primary and tertiary surface, a design so unusual that only one other telescope on Earth has attempted it. Behind that mirror sits the actual star of this story, the LSST camera. It weighs roughly 2,800 kilograms, about the weight of a fully loaded pickup truck, and it is physically the size of a small car, built to be the largest digital camera ever constructed for astronomy. Here's the number that should stop you. That camera captures images at 3.2 gigapixels. To put that in a size your phone can understand, a single Rubin photograph contains more pixels than 300 modern smartphone cameras combined. If you tried to display just one of its images at full resolution, you would need approximately 400 ultra-high-definition television screens arranged together just to see the whole thing without losing a single pixel of detail. Now, here is where it gets strange. That level of detail isn't the impressive part. What's inside the image is. The centerpiece of that first release was a single composite photograph of the Virgo galaxy cluster, built from roughly 10 hours of observations, collected across just 7 nights during the camera's earliest testing phase. 10 hours. That's less time than most people spend watching television in a single weekend. And inside those 10 hours of starlight, astronomers counted approximately 10 million galaxies, not stars, galaxies, each one containing anywhere from a few hundred million to several trillion stars of its own, each with its own planets, its own history, its own silence. Now sit with this number, because it's the one that actually explains why scientists went quiet when they saw it. According to NSF and NOIR Lab, those 10 million galaxies represent only about 0.05%, 1/20th of 1%, of what this observatory is expected to capture across its full 10-year mission. Rubin is projected to eventually observe roughly 20 billion galaxies before its survey ends. We looked through the door for 10 hours and already found more galaxies than most people could count in 100 lifetimes, and we're told that's barely a rounding error. But the galaxy count wasn't even the detail that made professional astronomers stop scrolling. Buried inside that same first-look data, moving against the fixed backdrop of stars, the observatory's software flagged something that hadn't been in any catalog the night before. In just those 10 hours of test observations, Rubin identified 2,104 previously undiscovered asteroids in our own solar system, 2,104 new objects found by accident, while the machine was technically still being tested. 7 of those newly found rocks were classified as near-Earth asteroids, meaning their orbits bring them into our planetary neighborhood. Scientists were quick to confirm that none of the 7 pose any danger to Earth. But that's not really the point. The point is the math. Ground-based and space-based observatories around the world, working together for an entire year, typically discover somewhere around 20,000 new asteroids combined. Rubin found over 2,000 in one weekend's worth of observing time, without even being switched into its real mission yet. How is a single machine outperforming the combined asteroid hunting effort of the entire planet in less time than it takes to binge a television series? The answer lies in something almost embarrassingly simple once you hear it. Nobody had ever pointed a camera this large, this sensitive, at this much sky, this many times in a row before. Every telescope before Rubin operated like a photographer with one perfect shot in mind. Pick your subject. Focus carefully. Take the picture. Move on. Hubble gave humanity extraordinary detail on individual objects. James Webb peered into infrared light from the earliest galaxies in existence, but neither of them was built to return to the same patch of sky, night after night, comparing what's there now to what was there yesterday. Rubin's entire design philosophy is the opposite of a single perfect photograph. Its real mission, called the Legacy Survey of Space and Time, is built to scan the entire visible southern sky roughly every 3 to 4 nights, over and over, for 10 straight years, which means that first release wasn't the finished puzzle. It was barely the box lid. And inside that same first look event, the observatory released something that had nothing to do with counting objects and everything to do with reminding people why we look up in the first place. Alongside the Virgo cluster image, Rubin published a composite photograph of the Trifid Nebula and the Lagoon Nebula, 2 glowing clouds of gas and newborn stars sitting roughly 4,000 to 5,000 light-years from Earth. Light that left those clouds around the time early human civilizations were first inventing writing is only now, this year, finally reaching a mirror in Chile. The image showed threads of dust and radiation-lit gas in colors so precise that astronomers could point to individual pockets where new stars are actively being born right now, gravity slowly folding raw material into the next generation of suns. It's the kind of image that doesn't advance a research paper. It just reminds you that the universe is not a still photograph. It is alive, constantly changing, and we are only now building instruments patient enough to notice. That patience requires an almost incomprehensible amount of data, and this is where the story stops feeling like astronomy and starts feeling like an infrastructure problem nobody has solved before. Once the observatory reaches full operational speed, it is expected to generate around 20 terabytes of new imaging data every single night. 20 terabytes is roughly equivalent to about 20,000 hours of high-definition video, more footage than one person could watch continuously for over 2 straight years, created in a single night, and then repeated again tomorrow and the night after that, for a full decade. Across its complete 10-year survey, scientists estimate Rubin will generate somewhere in the neighborhood of 500 petabytes of data. Try to hold that number for a second. 500 petabytes is enough storage capacity to hold roughly 500,000 full-length feature films in the highest quality available today. One observatory on one mountain is expected to produce a digital record of the sky larger than the entire combined film libraries of every major streaming service on Earth. Behind that camera sits a focal plane built from 189 individual sensors, each one so sensitive that NSF engineers have described its resolving power in almost absurd terms. theoretically capable of detecting something as faint as a candle flame from roughly 24,000 kilometers away, a distance longer than the entire circumference measurement most people learned for planet Earth in school. That is the level of faint light this machine was built to notice, and it noticed it on its very first real attempt. So why build something this extreme? Why aim a car-sized gigapixel resolution, planet-spanning sensitivity camera at the sky for 10 uninterrupted years? The answer takes us back to the person this entire observatory is named after, and to a mystery she stumbled into more than 50 years before this camera ever took its first picture. In the early 1970s, an American astronomer named Vera Rubin, working alongside physicist Kent Ford, pointed a far more modest telescope at the Andromeda Galaxy and began carefully measuring how fast stars near its edge were moving compared to stars near its center. Basic physics predicted that stars farther from a galaxy's core should move noticeably slower, the same way outer planets in our solar system orbit the sun more slowly than inner ones. That's not what she found. Stars at the outer edge of Andromeda were moving just as fast as stars deep inside it. According to the visible matter alone, Andromeda should have been flying apart, stars slingshotting off into the void. It wasn't. Something invisible had to be providing extra gravity, holding those outer stars in place, something with mass but no light of its own. That invisible influence is what we now call dark matter, and Rubin's careful, patient measurements became some of the strongest early evidence that it wasn't a theoretical curiosity. It was real, and it was everywhere. She never lived to see an observatory carry her name into operation, passing away in 2016, 9 years before this camera ever opened its eye. But every photograph this machine takes is, in a very real sense, still chasing the same question she first asked. What is actually holding the universe together, if most of it can't be seen at all? Here is how the observatory plans to finally answer that. As light from distant galaxies travels across our expanding universe, it stretches, shifting toward the red end of the visible spectrum, a measurable effect called redshift. The more stretched that light becomes, the farther away, and the further back in time its source must be. By carefully measuring this shift across billions of galaxies simultaneously, a method called photometric redshift, scientists can begin mapping exactly how mass, including the invisible kind, is distributed across the universe. Over its full 10-year run, Rubin is expected to measure redshift data for roughly 4 billion individual galaxies, out of the 20 billion it will ultimately observe. That's 4 billion separate distance measurements, each one a small brick in a map of the invisible skeleton holding galaxies, clusters, and superclusters together across unimaginable distances. Nobody has ever attempted to build a map at that scale before, because nobody has ever had a machine capable of collecting the raw material fast enough. And there's a second invisible mystery this observatory is hunting simultaneously: dark energy, the still unexplained force that appears to be accelerating the expansion of the universe rather than letting gravity slow it down. Scientists track this by studying type 1a supernovae, a specific and predictable kind of exploding star that acts almost like a cosmic ruler. In the late 1990s, 2 research teams studied fewer than 100 of these exploding stars and discovered the accelerating expansion in the first place, a finding that eventually won a Nobel Prize. Once Rubin's full 10-year survey reaches operating speed, scientists project it will identify around 250,000 type 1a supernovae every single year. Not 100, 250,000 annually for a decade. That flood of new data could finally help resolve one of the most stubborn disagreements in modern physics, a mismatch called the Hubble tension, where measurements of the early universe and measurements of the present universe stubbornly refuse to agree on exactly how fast everything is expanding. Think about the distance between those two numbers for a second. 10 hours of test observations already produced 10 million galaxies, over 2,000 new asteroids, and 2 glowing nurseries of newborn stars thousands of light years away. And that was before the real mission even started. The full 10-year survey hasn't truly begun stretching its legs yet, and it's already positioned to potentially settle arguments in physics that have lasted for over 2 decades. So what happens to our sense of the sky once this machine has been running uninterrupted for a full year? For 5 years? For all 10? Every previous generation of astronomers worked with a sky that felt fixed, frozen constellations, stars in the same place your grandparents saw them and their grandparents before that. It felt permanent because our tools were too slow, too narrow, too limited to catch it changing in real time. The Vera Rubin Observatory's first images already proved that assumption was never true. The sky was never still. We simply never had a memory large enough, fast enough, or patient enough to notice it moving. Now we do. And in the first 10 hours it was ever allowed to look, it found more than 2,000 pieces of our own solar system nobody had ever seen, 10 million galaxies stretching back across unimaginable cosmic time, and glowing stellar nurseries actively building the next generation of stars right now, tonight, while you're watching this. This telescope has 10 years left to run. What it captured in its first 10 hours was never meant to be the discovery. It was meant to be proof that the method works. So ask yourself the question these astronomers are already losing sleep over. If a single test image contained this much, how much of the universe has been sitting quietly above us this entire time, waiting for something patient enough to finally notice? If this story changed the way you think about the sky above you tonight, that quiet, unmoving canvas you've looked at your whole life without realizing it's been changing the entire time, then you already understand why this observatory matters. Subscribe if you want to be there for what it finds next, because this was only the first 10 hours of a 10-year story, and comment below with the number that stopped you the most. The 10 million galaxies, the 2,104 asteroids found in a single test run, or the fact that we're only 0.05% of the way through what this machine is going to show us.